All right, so this is a chapter 10 worksheet review. So let's walk through this a little bit. You can see my screen all right, if you can. So a couple things, let's start with going over some vocabulary. First of all, in a related sample, also called the dependent sample, participants are related. Participants can be related in one of two ways. They are observed in more than one group, which is a repeated measures design, or they are matched. Sure, I have the microphone here, so I think we can have really good quality recording coming in here. And we'll just go like this. That should make the recording a little bit better. Let's double check. Can you guys hear me? I think you can hear me. And we have a better microphone. Okay, hopefully that is going well. Yep, okay, cool, awesome. Just making sure that it's recording. Anyways, let's start from the top. All right, in a related sample, also called a dependent sample, participants are related. Participants can be related in one of two ways. They are observed in more than one group, a repeated measures design, or they are matched experimentally or naturally based on common characteristics or traits, which is a matched pairs design. The repeated measures design is a research design in which the same participants are observed in each treatment. Two types of treatment of repeated measures designs are the pre-post design and the within subjects design. The pre-post design is a type of repeated measures design in which researchers measure a dependent variable for participants pre and after post treatment. FYI, there are two types of designs for selecting related samples, are the repeated measures and the matched pairs designs. In the matched pairs design, participants are matched based on the characteristics that they share. Matched pairs can be obtained either experimentally or through natural occurrence. In a repeated measures design, the same participants are observed in each treatment. Two types of repeated measure designs are the pre-post and the within subjects design. Computing difference scores prior to computing the test statistic reduces the error by eliminating one possible source of error, thereby increasing the power of a hypothesis test. The degrees of freedom for the related samples t-test equal the number of different scores minus 1, degrees of freedom, and d minus 1. Two assumptions for related samples t-test are normality, and when I say normality, I mean normality like this. This is normality right here. Normality, okay, regular bell-shaped curve. All right, so just to be clear about what normality is, and going back here. And independence within groups, so they're independent of each other. Some definitions: the within subjects design is a type of repeated measures design in which the researcher observe the same researcher, in which the researchers observe the same participants across many treatments, but not necessarily before and after a treatment. The matched pairs design, also called the matched subject design or matched samples design, is a research design in which participants are selected and then matched experimentally or naturally based on common characteristics or traits. The related samples t-test is a statistical procedure used to test hypotheses concerning two related samples selected from populations in which the variance in one or both populations is unknown. A difference score is a score or value obtained by subtracting one score from another. In a related samples t-test, different scores are obtained prior to computing the test statistic. For a t-test, the term error refers to any unexplained difference that cannot be attributed to or caused by having different treatments. The standard error of the mean is used to measure the error or unexplained differences in statistical design. The estimated standard of error for the difference of scores, or S sub m, is an estimate of a standard deviation of sampling distribution of mean difference scores. It is an estimate of the standard error or standard distance that the mean difference scores deviate from the mean difference score stated in the null hypothesis. Example 1. One area in many areas of psychology and in education is an understanding and promoting reading among children and adults. Suppose we conduct a study with this area of focus by testing if teacher supervision influences the time that elementary school children read. To test this, we stage 2, 6, minute reading sessions and record the time in seconds that children spend reading in each session. In one session, children read with a teacher present in the room right here. In another session, the same group of children read without a teacher present. The difference in the time spent reading in the presence of the teacher versus the absence of a teacher is recorded. So teacher present, absent, difference. That's what we're looking at here, the difference between the absence of the teacher or the teacher present. So step one, we want to state those hypotheses. Because we are testing whether or not equal or not equal to a difference exists, the null hypothesis states that there is no mean difference, and the alternative hypothesis states that there is a mean difference. Therefore, the null hypothesis is that the mean difference is equal to 0. That means there's no mean difference in time spent reading in the presence versus absence of a teacher. And then the alternative hypothesis is that it's not equal to 0. There is a mean difference in time spent reading in the presence versus absence of a teacher. So a null hypothesis is usually no relationship. Alternative hypothesis is usually some sort of relationship, usually above or below the mean difference in this example. So FYI, the null and alternative hypothesis are making statements about a population of mean difference scores. Step 2, set the criteria for the decision. The level of significance is 0.05, and this is a two-tailed test for the mean difference between two related samples. The degrees of freedom for this test are degrees of freedom is equal to 8 minus 1, which is equal to 7. We locate 7 degrees of freedom in the far left column of the unit normal table, which is posted in normal table, which is absolutely posted in the news items. Move across to find the critical value for 0.05 proportion and two tails. The critical values for this test are plus or minus 2.365. And the way you might think about looking at that, or sort of graphically thinking about that, might be kind of like the following here. So what we have is we have what would be called our rejection region. So if we do a new share here and we go back to our whiteboard, what you have is, so we have this right here. So this is right here, and it's like the shaded area. We'll shade that, okay? And we'll shade this area right here, okay? Basically like that. And what we're saying is negative 2.365. And like I mentioned, it's right at it or greater. That is your rejection region, okay? You're gonna reject it. Rejection region. Actually, I'm gonna pause this for a second. I'm just gonna see if I can get a better tool to draw on the whiteboard. All right, so let's go back to the whiteboard here. Okay, in terms of what we're looking at. So this right here is your plugged in. All right, let's try the other technology. All right, so we'll go back to what we're doing here. So on the whiteboard, so this is your 2.365. So that's the same thing. That's also the rejection region over here. This is the retain. We're talking about, when we say retain, we're talking about the null hypothesis or reject the null hypothesis. So anything beyond the value, and actually at either right at or beyond is where you reject it. So let's go back to our desktop here. All right, so we locate 7 degrees of freedom in the far left column of the unit normal table. Move across to column from the critical values of 0.05 proportion of two tails. The critical values for this test are plus or minus 2.365. We will then compare the value of the test statistic to these critical values. If the value of the test statistic falls in either critical value plus or minus 2.365, there is less than a 5% chance that we would obtain that outcome if the null hypothesis were true. So we'll reject the null hypothesis. Otherwise, we're going to retain it because we're talking about our 95% probability of it being true because of alpha level being 0.05. 0.05 alpha level plus 0.95 equals 100%. So the next thing we do is we want to compute the test statistic. To compute the test statistic, we compute the mean variance and the standard deviation of the difference of the scores, compute the estimated standard error for the difference, and then compute the test statistic. So first, we're going to compute the mean, variance, and standard deviation of the scores. Keep in mind that the sign, negative or positive, the difference of scores matters when we compute the mean and standard deviation. To compute the mean, we sum the differences of the scores and divide by the total number of scores summed. So the mean difference of scores is equal to the sum of the difference divided by the population difference. So if we go back up here, we sum the difference right here. Okay, that's going to give you the 120. Then we divide it by 8. Where do we get 8 from? Number of participants, basically our population or sample. That's going to equal 15. To compute the variance, we use a computational formula. And that formula is right here. So to compute the variance, we use computational formula, which is literally this formula right here. I can certainly whiteboard this just so you have a good walkthrough here, which is going to be the computational formula for variance, which again will be the sum of the squares over n, or the sum of the difference of the squares over n, where the sum of the squares, which talking about this right here. We start with the sum of the squares over n for our variance, okay? But because we're looking at the difference here, we're going to say the sum of the difference is equal to the sum of the squares over the difference between the population minus 1. So the sum of the squares is equal to the sum of the difference times 2. So if we look at this, let's see if I can show you the difference up here. So let's take this right here, and I feel like if we put this in Excel, it's going to make a lot more sense. So let's go ahead and stop our share. Let's open up Excel, and let's do File, New. Okay, and we'll move this book over here. All right, and let's go back to desktop. Okay, so I'm just going to move that information into Excel. Okay, so all I did is I just took that information out of the Word document. Now we have our difference. So if we want to look at our difference in the scores and we want to sum that, we literally just go sum like that. That's 120. Okay, that's great. So that's going to be equal to our sum like that. It's literally sigma difference. And then what we need to do is we need to square these. So remember the sum of the squares. So we're going to square the difference, squared difference. Pretty easy conceptually, just to walk through it. This is the difference. I'm going to square the difference. So I'm going to take this right here, and I'm going to go equals E3. Nope, I want to equal D3. D3. That to the second power squared. Pretty straightforward. And then we're going to square all of those, which you can do by just filling down. Now those are all squared. Now we need the sum of all of those, which is our sum of our squares, which is equal to ED squared. Sum of the difference squared. ED squared. Okay. So sigma difference squared, which is 3,400. So now, if We go back to our Word document, which I believe you can still see, but I'll do a new share just in case, since the class is non-live. So if we go back to where we were, that's where I'm getting that from. The sum of the squares is equal to 3,400 minus 120 squared over 8. And the formula for computing the variance should look kind of like this. Yeah, make this a little bit bigger. And I think I can probably write this down here. The sum of the squares is equal to S, so for the variance, the sum of the squares over the n difference minus 1, where the sum of the squares is equal to the sum of the difference squared minus, on our numerator, the sum of the difference squared over the difference of the sample population. Therefore, the sum of the squares is equal to 3,400 minus 120 squared over 8, which is equal to 1,600. And this moved over here, okay? This was this right here, the 120. The 120 squared. No, it's like hard. That's 120 squared, okay? I can make that a little bit bigger. This right here is this 120 squared, okay? So just so you can see that, okay? Divided by 8, 3,400. There, which equals 1,600. So we'll move all this over here. Therefore, S squared D is equal to 1,600 over the degrees of freedom, so 8 minus 1, which is 7, which is equal to 228.57. And for the standard deviation, all we have to do is take the square root. So let me erase some of this just so you can keep going here. And then I'm going to show you where this is on the Word document next, okay? So then we take this right here, and we're going to go this direction, like that. And we're going to say that the SD, or our standard deviation, or our standard deviation difference, okay, is equal to the square root of S2D. Now we already have that. It's this number right here. So we're just going to plug this in right here. And the square root of 228.57 is equal to 15.12. And then if we want to get the standard error for the difference of the scores, the standard error difference between the scores, SMD, that's going to be equal to the standard, you take the square root, we substitute our standard deviation difference, which we have right here, divided by the square root of N, or our population difference. Their ND should be, I'll erase that. This should be like ND. Therefore, that means 15.12 divided by the square root of 8, which will equal 5.35. So let's go back to our Word document here. So that's literally what we did, okay? We did this, the sum of the difference of the squares divided by nd minus 1, where sum of the squares is the sum of the difference minus sum of the difference squared over the sample or population difference. It's 34 minus 120 squared divided by 8, 1600. SD2 is 1600 divided by 8 minus 1, 228.57. Compute the standard deviation, you take the square root of the variance. So we take the square root of 228.57 is equal to 15.2. And then to compute the estimated standard error for the difference in scores, we substitute 1512 for the standard deviation difference and 8 for the population or sample difference. 15.2 divided by 8 is equal to 5.35. So next we want to compute the test statistic. So we substitute 15 for the mean difference, for 0 for your mean difference. This is the value stated of the null hypothesis. So, and 5.35 for the standard error for the difference in scores. This is the standard error for the difference in scores, SMD. So you take the t obtained value, because we were trying to figure out what the t obtained value is against what we already found over here, okay? So we're going to compare this. So like, look at this right here, okay? And then we're going to figure out the t obtained value and compare it against the t statistic. So t obtained value is the mean difference of the sample minus the mean difference of the population. So it's 15 minus 0 because it's a null hypothesis divided by the standard error for the difference of scores, 5.35, and we get 2.804. So let me highlight that. So now we need to make a decision. To make a decision, we compare the obtained value. This is our obtained value right here that we just did to the critical value, which is up here. This is our critical value. And we want to see where that is on the rejection region. So we do that, we end up rejecting the null hypothesis. If the obtained value exceeds the critical value, the decision is to reject the null hypothesis. So 2.804 and 2.365. So graphically, what ended up happening is if you look right here and you go into this right here, let me move this out of the way. We had our bell curve, okay? And our critical value or our t value was 2.365, okay, plus or minus on either side. There's a two-tailed test. These are two tails right here. So we're going to say it's either here or over here. Now, because we had 2.804 for our t obtained value, because this was greater, because that was 2.804 was greater than 2.365, we know that it was further out here. So it was at or beyond this number, because it was 2.804. That's our rejection region. So that means we're going to reject the null hypothesis. That's why. So the next thing that I asked you to do on our worksheet is to literally walk through the same exact steps doing the calculations, same scenario, different data. So same idea, just different data. And then the last thing we do, yeah, that's it. The last thing we do is SPSS 10.4. So let me go ahead and pull up SPSS. I'll pause it and then I'll get this recording posted for you guys. All right, so let's talk about the SPSS aspect of this. So what we have right here, if you save the file from before, you could grab the chapter 11 because we did this just a little bit out of order. So all this is right here, this is literally the table that we just looked at in the assignment put into SPSS. You can do this as easy as you type this in, present, absent, make sure you have 0 on your decimals, you got your data view. It's literally that data, that's all we're doing. So what we want to do is we want to get the t obtained value, but we want to use SPSS, which is way faster, but it's important to know both SPS by hand as well as in SPSS. So we're just going to go compare means, and we're going to go to the paired samples t-test right here. We're going to go present variable 1, absent variable 2. Select. And then what we're going to do is we're going to move. So we move these pairs right here. We got that and that. And then, so these are side to side. So move these from the left box to the right box. And then we're going to say literally just okay. So it's a paired sample test. We say okay. And then we're going to get our statistics right here. And as you can see, our standard error of the mean is 5.345. Our mean is 15, which we just looked at in the worksheet. And our t obtained value is 2.806. Now you can use either do stuff by hand. You can also use SPSS on the exam. That's totally okay. But as you can see, that's much quicker. And then literally just going to save this as file, save as, and then you can say chapter 10 for worksheet, like that would be fine. And then save. And then also save the SPV file, because that's your output file, separate files, file, save as, chapter 10 for paired samples, maybe paired samples would be fine, something like that. So I know what it is when I'm looking at it. I can open these now. Like I said, if you want to export, you could tell it to export. You could attach it as a PDF. That would be fine. If it's a way to be a little more fancy about it. For me, I'll accept PDF files, Word files, as long as I can read it. SPSS is fine. I can absolutely read SPSS. But if you want to do like a PDF, you just go like that. Make sure you label it accordingly. You have the right file extension. So if you went like that, chapter, as soon as you put the information that went away, it'll basically export it. But like I said, it's absolutely fine if you save it as an SPSS file, so I can totally read those. So that takes us to the end of that worksheet. And then just I think a couple more things to just cover in terms of definitions here. Yeah, just a couple more things to cover, and then we'll get this posted for you guys. The mean difference and the estimated standard error for the difference of scores are entered in the formula for related samples t-test. The related samples t-test computed in the same way for repeated measures design. The related samples t-test is computed in the same way for a repeated measures design and a matched pairs design, and the standard deviation of the different scores is used to estimate the population standard deviation for the formula for Cohen's d. Proportion of variance is computed in the same way for all t-tests. So hope you learned something. Hope that was helpful. Make sure we're sharing here. Again, the mean difference for the estimated standard error for the difference of scores are entered in the formula for related samples t-test. The related samples t-test is computed in the same way for repeated measures design and a matched pairs design, and the standard deviation of the difference of scores is used to estimate the population standard deviation in the formula for Cohen's d, and the proportion of variance is computed in the same way for all t-tests. All right, so we'll get that posted. Hope you learned something, and I will see you in the next video. Call, text me, email me with any questions, thoughts, or concerns.